evolve. And as we keep moving forward, this bacteria started to feed on those plankton, and we started to remove oxygens. Water was left behind with a lot of carbon and hydrogens. And this is where we have these hydrocarbons, perfect ingredients for oil, C and H. And over the next 380 million years now, things were piled up, so sediment. And the sediment is perfect for trapping oil. And I can't stress that enough. You need these perfect conditions. You need to have the life, but then you need to also have the proper sediment to trap it. Because if it's not trapped, it will just seep up and it will just kind of rise up and escape and it won't have the time and pressure. So you actually need to trap it properly. And so all this heat and pressure makes us oil. Now we're jumping into a little bit more current time of why do we have to actually drill this oil? Some places it's just right there, the oil sands, it's just sandy oil right on top. But why do we need to drill for some oil? And we see these oil derricks. Well, pretty simple is I just talked about these perfect conditions for trapping this oil and gas. Well, it's actually buried kind of more than just a few feet below the surface. So we need to break through these petroleum traps or this rock layer that's trapping it. And we need to actually get the oil gas out of the ground by drilling through these petroleum traps and essentially sucking out the oil or gas. So how do we get all this oil and gas out first when we don't actually know what's underground? So first geologists, way back when, 50, 60, 70 years ago, they were looking at the Earth's surface, but they didn't have the technologies like we do now to actually predict and model what is below the Earth's surface. So they had to do alternative means. They would look for these things called outcrops. It's essentially, it's a rock out of place and they would think, why is this rock out of place? And when we had this rock layer exposed, they would then drill and they would take a core sample of the earth and look at the layers of the rock and see if they could maybe predict, oh, here is some sand, here is some sedimentary rocks, oh, here's a metamorphic rock, oh, wait, we see a shale layer, and with shale, maybe there is oil and gas trapped. What you see here is what a drill core actually looks like, and it gives you clues of what is beneath it. And when you pair up different drill cores from different parts, you can start to predict maybe there might be some oil somewhere. And these cylindrical tubes are taken during this operations, and geologists would study these rock cores and they could identify what was the sources of these rocks. Sometimes fossils may be present in these core samples too. As technology got better, we started to actually see seismic waves. And so not just earthquakes, because we can't predict when earthquakes happen, but we actually start to see when seismic waves and we could control seismic waves. And using this and how we understand seismic waves, we could actually send our own waves through the surface of the earth and we could predict how these waves actually transfer and they might use a vibration truck or they might use dynamite to send out a wave that they could actually read. And so seismology is actually how to study these waves of energy that move through Earth. And so one way is a vibrating truck or vibrating plates and having these explosions. Another way is tectonic activity. However, one way we can control, the other way we are not allowed, or we just can't predict when or where uh, earthquake will happen. And so the way we need to do it is use explosions or vibrating plates to read how these waves are traveling, and then we can kind of guess what are the rock layers without drilling all over the place. So two key terms we have are a seismograph and a seismogram. And so two terms of how we record and how we have a record of these seismic waves. And we're going to get something that looks like this. And hopefully we've worked through our earthquake lab and I'm going to give a little background now. And we see these waves and you can see it starts off slow and as the time kind of goes through, and we start to see waves pick up, and then it drops, and then all of a sudden we get a register on our seismograph, and all of a sudden it's picking up huge waves, and then the waves stop and taper off. So, like I said, earthquakes are hard to predict. There are other sources of seismic waves. If it's not man-made, it's coming from these earthquakes. And from our textbook, you can see how these plates rub up against each other or hit each other. And you can see there's Canada and Alaska, and right along that BC boundary or that BC coast, there's that big Pacific plate rubbing against the North America plate. So they're kind of like two blocks sliding against each other. So it's not one ducking under for the North American and Pacific plate until it gets underneath and it dips underneath Alaska. If you'd like, please open the notes, click on the link, and it takes you to a video of this Alaskan earthquake in 1964. Interesting side note for videos was actually on March 31st, there was an earthquake in Idaho, so kind of close to Calgary. And people in high-rise buildings downtown, people in BC, actually said they felt or they noticed a slight swaying. So people in high buildings felt like the building was kind of moving, or people in BC, there was a news report that they actually started to see their above ground pool starting to slosh and react to these seismic waves. So most people didn't feel it unless you're in some certain areas, but apparently it was a 6.5 earthquake right close to us in Idaho. Okay, now I have a few terms. I'm going to click through them first. Please make sure fill out your work booklet, and I'm going to talk about how all these terms work together on this next slide. And this is going to help with our terms for our earthquake lab. And so now we see here are our terms coming together where we have a fault line, and that's the big diagonal line coming straight across is our fault line. And first is the focus, and that's where we actually have our focus of the earthquake. That's the focus point. What we see now, though, as we go up, we actually see the epicenter, and the epicenter is not necessarily where the earthquake originated from, but this is where we are feeling directly above on the surface level. Okay, so we have some terms: the fault line, the focus, the epicenter. Please make sure we're reviewing what these terms are and what they mean. We have two types of seismic waves. First wave that we have is a P wave, and it's very easy to remember. It's the primary wave, meaning it's the first wave to actually come through. And so here are the details for a P wave. Okay, we have to make sure that we know what these P waves are and how they move. And by knowing some of the details of these P waves and how they actually travel, we're actually able to read them on a seismogram and how we can actually measure where earthquakes originated from, because we don't just have one central recording station. There is seismographs all over the place recording information, and by comparison and then by triangulating, by making those circles just like you did in your earthquake lab, people can figure out where the epicenter is and then figure out where the focus of these earthquakes are. So our P wave, though, are these longitudinal vibrational waves, meaning the particles are parallel to the direction. And this image next helps make more sense of it. And you see it's kind of like this compression wave. And so as the wave travels, it compresses, and then it kind of expands, and then it compresses. It's imagine if you took a slinky, sat it on top of a table, and pushed it, and you could see a wave. And if you could control it and have it not go as that typical up and down wave, but if you gave it a push, and you could actually see a wave travel through it. So it's kind of this compression or this pushing wave. Our second type of seismic waves, so we have two types, primary wave and secondary wave, very aptly named. This is the second wave to actually come through. And so this moves through solids only, make sure to know those key details. P waves travels through everything. S waves moves slowly through solid only, and it needs to be solid, okay? You'll understand once we look at how the waves travel, it doesn't really work through liquids. And so with this S wave, it actually has this amplitude and it's this up down motion, and it's what we typically think of as a wave. It's when a wave happens and it's this up and down actual motion. So you can't really have that traveling through a liquid. You see ripples on top of liquids, but when it's traveling through it, you don't see this up and down. And we call this a transverse wave, in which the vibrations of these particles, they're perpendicular, so it's going against the wave or the way it's traveling. Here we see the amplitude, and this is where we talked about the amplitude back in our earthquake lab and when we look at data. And so what we see here is how we have the amplitude of this P wave, where it first arrives. We have this interval time, and then we have the S wave arrive. So there's when we first record the earthquake from a distance. Obviously, it's 0 time is when it first starts recording it, and different spots on the earth will record it at different times. And depending how far away you are, the time between this P and S wave arrival can tell you how far away it is. And this is very important. Obviously, if you're very close to the epicenter or close to that focus, your S and P interval are going to be very, very small. However, somewhere like Calgary, you're going to feel the P wave come in, it'll register, and then all of a sudden you're hit with this S wave, and that's where we actually feel it, and it actually has the power. And that's where you see these amplitude lines up there and up there. You can see how big the wave is. With this interval, like I said, we can determine how far away we are. So depending how great and how far apart these wave intervals are, determines how far away we are in kilometers. And so you can see from here to here, roughly, when we match up this space, and if we could take this and match it up, let's say here to here, if they're 5 minutes apart, you might be 4,000 kilometers away. It might be in the matter of seconds, or it could be in minutes. Another detail about seismic waves, remember I talked about how P waves can travel through everything, the solids and liquids, but the S waves can only travel through the actual solid material. And so you see how you can have P waves and they can travel all the way through Earth, but these S waves can only travel through the solid mantle. And so there's a range of where earthquakes can be read globally. So finally, what happens? Because not all earthquakes are happening right at the surface, and not all earthquakes are focused right there. What happens the deeper we go? Well, as the depth of the earth increases, the speed of these waves also increase. And so if we saw that previous image where we went back and you saw how they transfer and they change through different mediums. And so waves travel at different speeds through different materials, whether it's rock, different types of rock, or if it gets into that core where it's liquid rock. And so this is because the earth is more dense. And so as it's more dense, the faster they can actually travel because the particles actually can push and they can move, and the waves travel faster through more dense materials, but not in straight lines in liquids, and it gets a little bit kind of rocky, if you will. And so here's just some details. Please make sure to fill them out on your workbooks. Lastly, a tsunami. And so one of the other big natural disasters that can happen from an earthquake. Yes, that's right. A huge giant tsunami tidal wave happens because seismic waves, they're set off underneath in an ocean basin. And what we're actually seeing is this force or this power pushing a lot of this ocean water. And please click the link, watch a video of what happens with tsunamis. Now that we've gone over some of the details of it and we've understood what P waves are, S waves are, we need a way to measure them, and that's this Richter scale, and it's used to measure earthquakes. Big important thing, I talked about it in my earthquake lab help, but how the Richter scale works is it is not just linear, meaning just 1 to 2 to 3, and they're all equally spaced. The difference between 1 and 2 is the same as the difference between 2 and 3, or 1 is half of 2, 2 is half of 4, right? It's not linear. What I'm talking about is 1 is there, but 10 times more powerful is 2. 3 is 10 times again more powerful. So the difference between 1 and 2 is 10. The difference between 1 and 3 is 100 times. And so it's not just jumping up linearly where it's just 1, 1, 1. It is 10, 100, 1,000, 10,000. And so you can see as you get higher and higher on the Richter scale, the numbers become even more powerful. And so this is good for comparing and categorizing earthquakes because I mentioned that earthquake that happened in Idaho on March 31st was 6.5. It's a big jump up if it's 7.5 or 5.5. Okay. What we see is if we're right near the epicenter of it, a 3 is barely detectable. That Alaskan one that I had the video to was a 9.2. Very, very dangerous. And you can imagine, we had a 6.5 in Idaho. Jumping up to a 9.2, that's almost 1,000 times stronger.